Hi everyone. We are now in topic 41.4 of our basic calculus subject, which talk about limits of polynomial, rational, and radical functions. The competency is at the end of this session. You are expected to apply the limit laws in evaluating the limit of algebraic functions, polynomial, rational, and radical. In previous lesson, we presented and illustrated the limit theorems. Now, we will be starting to recall these limit theorems. Let's see K, L, and M be real numbers, and let f of x and g of x be functions defined on some open interval containing C, except possibly at C. Number 1. If limit of f of x exists, then it is unique. That is, if f of x is equal to L and limit of f of x is equal to M as x approaches C, then L must be equal to M. Okay, so let us recall that, for example, if limit of f of x as x approaches C is equal to 5 and limit of f of x, limit of f of x as x approaches C from the left is equal to 5 and limit of f of x as x approaches C from the right is equal to 5. Therefore, since the two limits are equal, so we can say that the limit of f of x as x approaches C exists and is equal to 5. Okay, the number 2 is the limit of C as x approaches C is equal to C. Again, if we have the limit of 6 as x approaches negative 2 is equal to 6. Okay, then the next one, number 3, states that the limit of x as x approaches C is equal to C. For example, we have the limit of x as x approaches negative 2 is equal to negative 2. And then number 4, suppose that limit of f of x as x approaches C is equal to L and limit of g of x as x approaches C is equal to M. So for constant multiple, if we have, for example, or the theorem is the limit of k times g of x as x approaches c is equal to k times m, because the limit of g of x as x approaches c is m. So for example, if we have the limit of 5 times g of x as x approaches 3 is equal to, okay, for example, if the limit of g of x as x approaches 3 is equal to 8. So substituting, so we have 5 times 8 is equal to 40. Okay, so this 5 here must be multiplied to the limit of g of x as x approaches 3. Okay, then we have also the what we call as addition theorem. Okay, and let us say the limit of f of x as x approaches 3 is equal to negative 2. So in order to find the limit of f of x plus g of x as x approaches 3 is equal to negative 2 plus 8, or 6. And the limit of f of x minus g of x is equal to negative 2 minus 8 is equal to negative 10 as x approaches 3. Okay, and the limit of f of x times g of x is as x approaches 3 is equal to the product of the limits, that is negative 2 times 8 is equal to negative 16. Okay, and then the limit of f of x over g of x as x approaches 3 is equal to 8 over negative 2, or equal to negative 4. If we let that the limit of f of x as x approaches 3 is 8, and the limit of g of x as x approaches 3 is negative 2. So getting the quotient of the two limits, the answer is negative 4. Okay, and then if for example we have the limit of f of x to the second power as x approaches 3. So what are we going to do, since the limit of f of x as x approaches 3 is 8, then squaring that, so the answer is 64. And lastly, we have the limit of the inch root or the square root of f of x as x approaches 3. So in this case, we are going to find the square root of the limit of f of x. So that's why we have the square root of 8 is equal to 2 square root of 2. Okay. So let us now apply these theorems in evaluating algebraic functions. Particularly, he will illustrate how to use them to evaluate the limits of polynomial, rational, and chronicle functions. Okay, let us try to apply the theorems we learned in evaluating example number 1. We are going to determine the limit of 2x plus 1. Okay, so using addition theorem, to get the limit of 2x plus 1 as x approaches 1, it would be similar to the limit of 2x as x approaches 1 plus the limit of 1 as x approaches 1. So getting the limit of this would be similar to 2 times 1 plus the limit of the constant, which is 1. Therefore, this is similar to getting the sum of 2 plus 1 or equal to 3. Okay. So next is to find, or in number 1, the limit of 2x plus 1 as x approaches 1 is equal to 3. Okay, number 2 is to find the limit of the function 2x cubed minus 4x squared plus 1 as x approaches negative 1. From the theorems we learned last time, we are now to find the limit by applying addition property or addition theorem. We have the limit of 2x cubed as x approaches negative 1 minus 4, or the limit of 4x squared as x approaches negative 1 plus 1, limit of 1 as x approaches negative 1. Okay, so this one is similar to limit of x cubed as x approaches negative 1 minus 4 limit of x squared as x approaches negative 1 plus the limit of 1 as x approaches negative 1. Okay, in the first one we have 2 times the limit of this is similar to negative 1 to the third power, applying the power limit or power theorem, minus 4, replacing x with negative 1 times negative 1 squared plus 1, which is 2 times negative 1 minus 4 times 1 plus 1. Okay, so this is negative 1 because negative 1 times negative 1 times negative 1 is negative 1, and this one also is positive because we are squaring negative 1. So this is similar to negative 2 minus 4 plus 1, and negative 2 minus 4 is negative 6 plus 1 is negative 5. Okay, so number 2, the limit of 2x cubed minus 4x squared plus 1 as x approaches negative 1 is negative 5. Okay, so let's proceed to number 3, evaluating limit of 3x to the 4th minus 2x minus 1 as x approaches 0. So in this case, we are going to apply the addition law, which is, first we have limit of 3x to the fourth as x approaches 0 minus 2, or minus the limit of 2x as x approaches 0 minus the limit of 1 as x approaches 0. Okay, so this part is 3 limit of x to the fourth as x approaches 0. The second one is similar to the negative of 2 limit of x as x approaches 0 minus the limit of 1 as x approaches 0. So simplifying this one, it is similar to 3 0 to the fourth minus 2 times the limit, which is 0, and minus 1. Okay, it's the limit of the constant. So this is 3 times 0, because 0 to the fourth is 0, minus 0 minus 1. And this one is 0 minus 1, which is equal to negative 1. Okay, so therefore number 3, the limit of 3x to the fourth minus 2x minus 1 as x approaches 0 is negative 1. Okay, let us now apply the limit theorems in evaluating rational function. So in evaluating the limits of such function, we are to apply the division rule, and all rules were stated in the division rule, which have been useful in evaluating limits of polynomial function, such as the addition and product rule. Okay, so in number 4, we are going to evaluate the limit of 1 over x as x approaches 1. So take note that the limit of x as x approaches 1 must be equal to 1. So since the denominator will never be 0, so we can apply the division rule. No? So if the given function is rational, we will investigate first if the denominator is 0 or not. So in this case, so since it's not the denominator will never be 0 because the x will be approaching to 1, therefore we can apply the division theorem. So what are we going to do is the limit of 1 over x as x approaches 1 is similar to the limit of 1 as x approaches 1 all over the limit of x as x approaches 1. So the limit of 1 as x approaches 1 is 1, using the constant, over the limit of x as x approaches 1 is also equal to 1. Therefore, the limit of 1 over x as x approaches 1 is 1. Okay. Next is we are to evaluate limit of x all over x plus 1 as x approaches 2. So investigating the denominator when x is 2, therefore it's 3. So that means we can apply the division theorem. Okay, so what shall we do is we have the limit of the numerator x as x approaches 2 all over the limit of x plus 1 as x approaches 2. Okay, so the numerator is 2 and the denominator is 2 plus 1 is 3. So therefore, the limit of x all over x plus 1 as x approaches 2 is equal to 2/3. Okay. Example number 6. Example number 6 is the limit of quantity x minus 3 times quantity x squared minus 2 all over x squared plus 1. Okay, take note that if we are going to replace or check the denominator and substitute x with 1, the denominator is not 0. So what are we going to do is evaluating the limits of each part. So it would be similar to the limit of quantity x minus 1, x minus 3 x minus 3 as x approaches 1 times the limit of quantity x squared minus 2 as x approaches 1 all over the limit of x squared plus 1 as x approaches 1. Okay. Numerator is similar to the limit of x minus the limit of 3, and both limits has value x approaching 1 times the limit of x squared as x approaching 1 minus the limit of 2 as x approaches 1. And this is divided by the limit of x squared as x approaches 1 plus the limit of 1 as x approaches 1. Okay, the numerator is the first quantity of the numerator is we have 1 minus 3 because the limit of x as x approaches 1 is 1 and the limit of 3 as x approaches 1 is 3 times the limit of x squared as x approaches 1 is 1 squared minus 2 all over 1 limit of x squared as x approaches 1 is 1 plus the limit of 1 as x approaches 1 is also 1. And this is 1 minus 3 is negative 2 times 1 squared is 1 minus 2 is negative 1 all over 2. So we have a negative 2 times negative 1 is 2 over 2, which is equal to 1. Okay, so that's why example number 6 is 1. Okay. Okay, example number 7. Number 7 is we are going to evaluate the limit of 2x cubed minus 4x squared plus 1 as x approaches -1. So notice that if we are going to analyze the first 6 example we have, it is quite similar to ato i-shortcut ang process. Same na sa idiretso na to replace ang atong values, no? To adto sa mga x and then i-simplify. So that's why that is similar kuno ang limit of f of x as approaches c is similar to f of c. So ato na lamang i-shortcut ang atong evaluation, no? So in number 7, evaluating limit of 2x cubed minus 4x squared plus 1. So in this case, the limit of 2x cubed minus 4x squared plus 1 as x approaches -1 is similar to 2 times -1 cubed minus 4 times -1 squared plus 1 is equal to 2 times 1 minus cube ni cube. So -1 cube is -1 times 4 times 1, -1 squared is 1, then plus 1. So this one is -4 and this one -2 and this one is -4 plus 1. So -2 minus 4 is -6 plus 1 is -5. So therefore the limit of 2x squared minus 4x squared plus 1 is -5. Okay. Next is example number 6. Number 8. Okay. Number 8 is about quotient, wherein if we are going to substitute the denominator with 1, ang x sa denominator with 1, it should be 1 plus 3 times 1 squared plus 4 times 1 to the 4th. It is similar to 1 plus 3 plus 4 is equal to 8. Okay, so let us check. Okay, 8 na no, so we can apply the division law because the denominator is not equal to 0. So in this case, finding the limit of 1 minus 5x all over 1 plus 3x squared plus 4x to the 4th as x approaches 1. Okay, so the numerator is similar to 1 minus 5 times 1 and the denominator is 8 is equal to 1 minus 5 is -4 over 8. Then the answer is -1/2. Okay, so the limit for number 8 is equal to -1/2. Okay, next is example number 9. We are going to evaluate the limit of the square root of x as x approaches 1. So take note that the value of the square root is undefined when x is less than 0. So if we are going to find the limit of square root of x as x approaches 1, and we replace the x with 1, so it will never happen that x is less than 0. So that's why we can immediately apply the radical or root rule. So finding the limit, we have the limit of this, finding the limit for the limit of square root of x as x approaches 1 is similar to the square root of 1, which is equal to 1. Okay, thus example number 9 is equal to 1. So let's proceed to example number 10. Example number 10 states that the limit of square root of x plus 4 as x approaches 0. So if we are going to replace 0 into x, so 0 plus 4 is 4, and the square root of 4 will not equal to a negative value. So that's why applying the radical rule, we have the square root of 0 plus 4, and the square root of 4 is equal to 2. Okay. Next is the limit of the cube root of x squared plus 3x minus 6. So we have the limit of the cube root of x squared plus 3x minus 6 as x approaches negative 2. So finding the limit, we have the cube root of negative 2 squared plus 3 times negative 2 minus 6. This is similar to the cube root of negative 2 squared is 4. Then 3 times negative 2 is negative 6 minus 6. So it would be the same as the cube root of negative 2 minus 6 is equal to the cube root of negative 8. So notice that the radicand here is negative, but the index of our radical is 3. So since 3 man, it's not even, therefore this one is defined. Diba? Masolve na to because it's negative. And the cube root of negative 8 is equal to negative 2. Okay? So, ma-undefined ra siya kung the index of the radicand is negative, the index is even, and the radicand is negative. Okay? So, let us proceed to example number 12. Example number 12 is about evaluating the limit of the square root of 2x plus 5 all over 1 minus 3x as x approaches 2. So evaluating the numerator, we have the square root of 2 times 2 plus 5 all over 1 minus 3 times 2. This will give us 4 plus 5 all over 1 minus 6. 4 plus 5 is the square root of 9 all over 1 minus 6 is negative 5. So square root of 9 is 3 over negative 5. So therefore, the value is the same as the negative of 3 over 5. Okay. So let us first proceed to infinite limits. infinite limit. So some functions take off in the positive or negative direction, increase or decrease without bound, near certain values for the independent variable. When this occurs, the function is said to have an infinite limit. Hence, we are going to write the limit of f of x as x approaches c is equal to the positive infinity, or the limit of the function f of x as x approaches c be equal to negative infinity. Note also that the function has a vertical asymptote at x equals c if either of the above limits hold true. So notice that last time there are situations wherein in our graphing analysis there is a situation that for example, the graph is half of the parabola opening upward, and there is also the left of 1 na apoy parabola opening downward, half of parabola opening downward. Okay, so ang nahitabo, di ba dire, for example, atong evaluate ang function of x as x approaches 1 from the left, kay wa man siya mo, as x gets closer and closer to 1, ang value nimo sa y is without bound, meaning wa siya mo stop, kay parabola opening downward man siya, or half of the parabola opening downward. So that means actually the limit is, or the limit does not exist, but klaro man siya nga extended towards ngadto sa downward, ngadto sa negative infinity. So that's why makaingon ta nga ang limit of f of x as x approaches 1 from the left is equal to negative infinity, whereas ang limit pod of f of x as x approaches 1 from the right pod nun mano, so it's positive infinity. So since negative infinity man o positive infinity, therefore the limit does not exist. But if pareha pa ni sila nga negative infinity pod, so we can say that the limit of f of x as x approaches 1 exists, and it is equal to negative infinity. Okay, so since kani silang duha kay na wa man equal in opposite direction man, therefore the limit does not exist. Okay, so mo to gitawag og infinite limits. So let's evaluate limit of 1 over x squared as x approaches 0. So if we are going to use the graph interpretation, so we can say that the limit of f of x as x approaches 0 from the left is positive infinity. Ba? So, as x approaches 0 from the left, ikan dari sa left sa 0, padung siya sa positive infinity. Whereas, if we are also to evaluate the limit of the function as x approaches 0 from the right, maugyapon nagtuyapon siya sa positive infinity. So that's why we can conclude that the limit of f of x as x approaches 0 is positive infinity. Okay, nanong naingunahin man ang hitabo. If we are going to replace x with, for example, negative 4, mahimo kasi siyang 1 over 16. Diba? Kung negative 3, mahimo kasi siyang 1 over 9. Negative 2, mahimo kasi siyang 1 over 4. And then, kung negative 1, mahimo kasi siyang 1. Okay, kung 1/2 imong i-substitute sa x, if x is 1/2, mahimo 1 over 1/4 or 4. Ano 1/2, 4. O pa dali, bali. Mga usa ka gihapon. So, mag-anam ka, dako ang value dire. Mag-anam po ka dako ang value. Kay negative man. Whereas dire, mag-anam ka gamay ang value, manam po ka dako ang y. So that is y extended towards positive infinity. Okay, so let us now consider the function f of x equals negative 1 over 2. 1 over x squared. So, okay. Negative naman, so mabali na po ang direction sa atong graph. Okay, so padong na po dire. That's why we can say that the limit of f of x as x approaches 0 is negative infinity. Why? Because the limit of f of x as x approaches 0 from the left is pointing to the ubos, and then from the right pole maugapon towards the negative infinity. Since they have the same man sila o limit, so therefore the limit exists and it is equal to negative infinity. Okay, let us now consider the f of x equals 1 over x. So notice that the graph informs us that when x is approaching 0 from the left, so dire towards 0, so padong siya sa ubos. And from the right pole of 0, ang imong value sa y is approaching to positive infinity. So since negative man ang sa left and positive pud ang from the right, so they do not have equal limits. So that's why ang limit of the function as x approaches 0 does not exist. Okay? So a quotient of f of x over g of x in which the numerator and denominator both have a limit of 0 as x approaches a is called an indeterminate form of type 0 over 0. So, ganina makita na to ang masolve na to ang value sa quotient of the function, the limit of the quotient. Dali ra tungod kay ang denominator is not 0. But what about kuno in the situation wherein mo 0 ang denominator and 0 po ang numerator? So what shall we do? So for example, if we are going to find the limit of x squared minus 1 over x minus 1 as x approaching 1. So notice that og ato substitute ang numerator with 1, 1 minus 1, it is 0, 0 over 0. So, manay itawag og indeterminate. So, ug ato ay analyze, notice that ang denominator is a factor of the numerator. So that's why we need to factor out if it is factorable. So factoring the numerator, it is similar to quantity x minus 1 times quantity x plus 1 all over x minus 1. So that we can cancel the x minus 1, and what is left is the limit of x plus 1 as x approaching 1. So evaluating the limit, we have 1 plus 1 is equal to 2. So in this case, the limit of x squared minus 1 all over x minus 1 as x approaching 1 is equal to 2. What about the second one? The limit of x minus 1 all over the square root of x minus 1 as x approaches 1. So again, when we replace the x with 1 in the denominator, 1 minus 1 is 0, and also in the numerator, 1 minus 1 is also 0. But since our denominator has radical, we can simplify it by rationalizing the denominator. To rationalize, we are going to multiply both numerator and denominator with the conjugate of the denominator, which is square root of x plus 1 over square root of x plus 1. So simplifying, it would be similar to the numerator becomes x square root of x when we multiply x times square root of x plus x times 1 is x minus the square root of x minus 1 all over the square root of x squared minus 1, because square root of x times square root of x is the square root of x squared. Then square root of x times 1 is square root of x. Next is negative 1 times square root of x is negative square root of x. That would be 0 na. Then minus 1 is similar to copy x square root of x plus x minus square root of x minus 1 all over x. Over x minus 1. Okay, but if we are going to analyze the numerator, kung wa pa to na to gi-simplify, kani this part here is actually quantity x minus 1 times this square root of x plus 1. No? Na-simplified na to. So, hindi na to i-simplify. Ma-cancel out ni na to. Okay. So, what is left is the limit of the square root of x plus 1 as x approaches 1. So, therefore, the answer would be square root of 1 plus 1 is equal to 1 plus 1 equals 2. So, that means na safe na nga nawa na ang katong mahimo siyang 0. But actually, nga to sa graph ni mo unja, kung imo tong i-graph, mahalo tong apart, mahimo siyang gitawag og vertical asymptotes ang kaning 1 nga value sa x that will make the denominator 0. So, mahimong vertical asymptote. Kaya dili man mo pass through ana because 1 there will make the denominator 0. Okay? Okay, so that will be all for this topic. So, naapay coming, which is 2.1 and 2.2. So, thank you for listening and God bless.